Hello teacher, my name is İsmail. Now I will explain how this Java function works and analyze its time complexity step by step. Let's start it. First of all, we have a function. The name is partial sum of squares. It takes an integer r and integer n, which represents the size of the array. We have array in here, and this one is explained the size of the array. So the purpose of this function is to iterate through the array, check for negative numbers, square them, and add them to the result. Finally, it returns the sum of squares of all negative numbers. Now let's look in the code. Let's go through this step by step. We declare an integer variable result in here and initialize it to 0. This will store our final sum. The loop starts from I equal to 0 and runs until I lower than n. It increments I by 1 each iteration in here. This means the loop will execute exactly n times, where n is the size of the array. Inside the loop, we should look here. We check if Ri is negative. If the condition is true, we square the number and add to result. In here, multiplication and addition are both constant time operations. So it's meaning they take O1 time. After the loop finishes, we return the final value of result, which is the sum of squares of all negative numbers in the array. I'm sorry. Okay. Now, let's analyze the time complexity of this function. The for loop runs n times, and each iteration performs only constant time operations. It's equal to O1. So the total time complexity is calculated as like O n multiply, let's see, like this, O n multiply by O1, because our constant time operations is O1, so it equal to O n. Since we ignore the constant factors in big O notation, the final time complexity remains O n, which means it scales linearly with the size of the input. For example, if n equal to 10, our loop runs 10 times. For example, n equal to 1 million, our loop runs 1 million times. So as n increases, the execution time grows proportionally. Our first question is clear. Let's talk about the second one. Let's start with second one. What are the time complexities of the following code fragments? In here, I will explain different types of loops and analyze their time complexities step by step. Let's talk about the first loop. In this loop, I equal to 0 and increments is I by 1 each time. It runs until I reaches n square n. So, how many times does it run? The loop starts at 0 and runs until n square n. N not square, I'm sorry. N multiply n. It equal to n square, right? So that means it executes exactly n squared time. So our time complexity is O n square. The second loop, let's see. This loop similar to first one. It's nearly similar to first one. But instead of increasing by 1, it increases by 40 in each iteration. We can see in here. So how many times does it run? The total number of iterations is roughly n square over 40. Since 40 is just a constant, it doesn't affect the big O complexity. So our time complexity is O n square, same like first one. Even though it runs fewer times than the first loop, the time complexity remains O n square because we ignore constants in big O notation. Let's talk about the third one. In here, this loop increments I by n each time. So instead of I or 40, doesn't matter. How many times does it run? The total number of iteration is n square over n. So our time complexity is O n. This loop runs much faster than the previous ones because I jumps by n in each step. Fourth one is we can see I starts at 10, so increases by 2 in each iteration and stopping at n square over 3. So how many it return? Does it run? The number of iteration is approximately n square over 3, like this, n square over 3 over 2, which simplifies to O n square. Our time complexity is this. So even though we divide by 3 and increment by 2, these are constants, so they don't affect the big O complexity. Let's talk about the fifth one. In here, this loop starts with 0 and runs until 1 billion. Yes, 1 billion. It's equal to 10 power of 8, which is a fixed number. So, how many times does it run? It always runs exactly 100 million times. Let's see. Not 100 million times, it's equal to 1 billion times, regardless of n. So our time complexity is O1. Since the number of iterations is a constant, this loop takes constant time O1. Let's talk about the sixth one. Here, I starts with 1 and doubles in each step. 1, 2, 4, 8. We can see in here. So how many times does it run? The values of I from the sequence 1, 2, 1, 2, 4. These are power of 2, right? 8, blah blah blah blah. It's going to n in here. So the number of times it's run is logarithm 2 n. So our time complexity is O log 2n. Not 2, I'm sorry. O log n. Since I is multiplied by 2 each time, the number of iteration is proportional to log 2n in here. So our time complexity is this. Let's talk about the 7th one. This loop starts at n and decreases by dividing by 4 each time. So if n is large, the loop never runs because n is already greater than 10 at the start. So our time complexity is O1. That's clear. This is a constant time loop since it either doesn't run or runs for a very small number of steps. So let's talk about 8th one. Now let's analyze the nested loops. There's a two different for loop, and this is the nested loop. So let's talk about the outer loop. It runs n over 100 times, which is O n. And inner loop is runs from m to 40, decreasing by 4 each time, so it's equal to O m. I can write like this, O m, and this one is O n. So our total complexity is O n m. Since the inner loop runs OM times for each iteration of the outer loop ON, the total complexity is ONM. Let's talk about the last one. There is another nested loop. So, but the outer loop follows a logarithmic pattern. So, in the outer loop, I starts with 1 and multiplies by 5 each time. So it's like 1, 5, 25, 125. These are 5's power, and this in this loop, our time complexity is O log n because of the power of 5. Inner loop runs from m over 2 to m over 2 to m, which is the Rowley m over 2 times. So in the second loop, inner loop, our time complexity is OM. So the total complexity is O m log n. Since the inner loop runs OM times for each O log n iterations of the outer loop, the total complexity is O m log n. this part also finished, so let's talk about the next part. Now, let's talk about the third one of this homework. In here, what is the time complexity of the following the power function? We just talked about that. In here, this function calculates the x power of n using recursion. Instead of multiplying x multiply n times, it used an optimization called exponentation by squaring, which reduce the number of recursive calls. Let's talk about the part of condition. If n is even, the function calls itself x multiply x and n over 2. In here, we can say like that. If n is odd, it does the same but multiplies by x one more time. Okay, we can see here. This effectively reduces n by half in each step. Let's talk about the time complexity. Since n is divided by 2, in each recursive call, the number of recursive calls is log n. So, therefore, the time complexity is O log n. Our time complexity is O log n. Our time complexity is this. Let's talk about the other part. In here, what is the time complexity of the following Fibonacci function? Let's talk about the Fibonacci function's time complexity. This function computes the Fibonacci sequence using simple recursion. For each n, it makes 2 recursive calls. One of the n minus 1, one with n minus 2. This leads to an exponential growth in the number of function calls. Time complexity is, let's talk about time complexity. Let Tn be the number of calls made. We can express it as Tn equal to Tn minus 1 plus Tn minus 2 plus O1. So this recurrence follows the Fibonacci sequence, leading to an exponential growth pattern. The complexity is approximately O to power of n, making the inefficient for large n. So a better approach is to use memorization or dynamic programming to reduce the complexity to O n. So let's talk about the last part of this homework. In here, we have 2 computers, okay? One of is a fast computer that is 10 times faster than a slow one. We have 2 different computers. A slow computer running 2 different algorithms, Fast algorithm with ON, time constant, time complexity. The slow algorithm one is O n square. This is the slow one, time complexity. Which one is faster? We can compare it with slow algorithm on fast computer. Since the computer is 10 multiplication faster, we approximate the execution time as O n square over 10. Fast algorithm on slow computer, this run in O n time complexity. For small values of n, the faster computer might compensate for the inefficient algorithm. However, as n grows larger, so O n square over 10 still grows quadratically, which becomes much worse than O n or large n. Thus, fast algorithm on slow computer is the better choice in the long run. Let's talk about the hardware speed. Algorithmic efficiency is more important than hardware speed. A bad algorithm will always perform worse than a good algorithm, regardless of computer speed. Optimizing algorithms should be prioritized over upgrading hardware. Thanks for listening. See you next time.